Now, here's the full TTS-ready transcript using these guidelines.
Okay, let's jump into something that might just surprise you. We hear constantly about AI breakthroughs, right? Bigger models, faster chips. But what if the next massive leap isn't about algorithms, but something, well, something much more fundamental?
You mean like just keeping the lights on? Or
Hmm.
rather keeping things from melting?
Exactly. Like, what happens when all this amazing AI power just gets too hot to handle? Today, we're doing a deep dive into thermal technology. It sounds maybe a bit dry, but it's this critical, almost invisible factor for AI's future.
It really is fascinating how this, seemingly basic engineering problem, heat, is right at the core of our most advanced tech. And we're
Hmm.
seeing serious money flowing into this area now, just figuring out how to cool these AI systems down.
Right. It's a massive challenge with potentially huge consequences if we don't get it right. So maybe you're an engineer, knee deep in system design, or maybe you're just curious about what's really driving tech forward. Understanding this heat problem, this thermal bottleneck, gives you a really unique angle on where AI is actually heading. Our mission here is simple: pull out the key insights, why thermal innovation isn't just like a nice to have, but absolutely vital for unlocking AI's potential.
And if you just look at the numbers, the growth in AI hardware is, well, it's explosive. Projections, I think, from IDC suggest global spending will top 1.6 trillion new Taiwan dollars by 2026.
Wow, okay. NT $1.6 trillion. What's that in US dollars, roughly?
That's around 50 billion US dollars annually.
50 billion a year,
Yeah,
just on the hardware. And AI isn't just in labs anymore, is it?
not at all. It's everywhere. You've got the huge cloud data centers, obviously.
Yeah.
But also, think about cars, autonomous driving systems, even edge devices like smart glasses or, those robots we're starting to
We're
see.
filtering down into everything.
And the core problem is physics, really. More computing power equals more heat. It's a direct link. We're talking about individual chips now hitting over 300 watts pretty regularly.
300 watts, like an old, bright, incandescent bulb, that much heat from one chip.
Yeah, and sometimes much more. Some of these new platforms, like NVIDIA's Blackwell, for instance, they're pushing towards or even past 1,000 watts.
1,000 watts. Seriously, that's like having a small heater baked right into the system.
It basically is. And the bigger the AI model, the more complex the calculations, the hotter it's going to run. It's inherent.
So it's not just a minor inconvenience, this heat?
Oh, definitely not. It's a major barrier. It directly impacts how well these AI systems can actually perform.
Okay, so we've got this boom in AI hardware churning out serious heat. What actually happens when it gets, too hot, when it hits that bottleneck?
Well, that's where you hit these thermal bottlenecks, as people call them. Think of it like uh, trying to push too much water through too small a pipe. The system backs up. Overheating causes a few big problems. First, systems often have to throttle back performance to protect themselves.
Throttle back, so they deliberately slow down. All that expensive computing power just gets hobbled.
Exactly. Hobbled is a good word. Performance drops. Plus, running hot constantly shortens the lifespan of the components. These are expensive parts, remember.
Right, so it costs more in the long run, too.
It does.
Yeah.
And in worst cases, too much heat just causes instability. Systems can crash.
So all that potential, that $50 billion a year investment, can literally be stopped dead by, well, by temperature.
Yeah.
Seems like we really need effective ways to get that heat out then.
We absolutely do. And that's where something called thermal interface materials, or TIMs, becomes so important.
TIMs, okay, thermal interface materials, what are they exactly?
They're basically the crucial link, the bridge, between the hot chip itself and whatever is cooling it like a heat sink or a liquid cooling plate.
Ah, okay. So they sit between the heat source and the cooler.
Precisely. Their job is to conduct that heat away from the chip as efficiently as possible and transfer it to the cooling system. They're kind of the unsung heroes of thermal management.
Unsung heroes, I like that. What form did they take? Is it like that paste you put on a PC processor?
That's one type, yeah. Thermal paste is common, but there are others like thermal pads, sort of squishy conductive sheets, and also gap fillers, which are designed to fill slightly larger or uneven spaces. They're all highly engineered materials optimized for heat transfer.
So it's not just slapping a cooler on top. Getting that interface right with the right TIM is critical for making the whole cooling system work effectively.
Absolutely critical. Without good TIMs, even the best cooler won't perform well. They ensure the AI hardware stays cool enough to run reliably and at its full potential.
And this whole cooling aspect, including these TIMs, it's becoming a bigger piece of the pie, economically
A
speaking.
much bigger piece. The analysis we looked at suggests cooling systems, and these TIMs can now make up over 20% of the total cost of AI infrastructure.
20%. Wow. So on a $50 billion annual spend, that's what, $10 billion a year just focused on cooling?
That's the scale we're talking about. It's a huge market, and it's growing right alongside AI itself. So the companies that are really pushing the boundaries in thermal management, developing better TIMs, better cooling, they're not just suppliers anymore.
They're more like enablers.
Exactly. Key enablers.
Yeah.
Their innovations directly impact what the next generation of AI can actually achieve.
That really shifts the perspective. Better cooling doesn't just stop things from breaking, it actually unlocks higher performance and more advanced capabilities.
It absolutely does. Think about, say, autonomous driving. You need instant processing of sensor data reliably all the
Yeah.
time. No throttling allowed.
Right. Failure is not an option there.
Or complex robotic surgery. Precision, stability paramount. Even the huge language models, the chatbots, they rely on massive compute power running consistently. How well you manage the heat directly sets the limits. Or, conversely, provides the launch pad for all these applications. Thermal control is both the cage and the key.
Okay, so wrapping this up then, for anyone listening who's working with AI hardware, maybe designing chips, building platforms, integrating systems, what's the main thing they should take away from this deep dive?
I think the core message is, don't just look at the chip specs, the teraflops, whatever. The actual real-world performance, the reliability, the longevity of your AI system, that depends just as much, maybe even more, on how effectively you manage the heat.
Hmm.
Your thermal strategy is critical.
That's a really crucial point. The power is useless if it throttles itself or crashes. Sometimes the most important stuff is, let's say, less glamorous than the algorithms. So here's a thought to leave you with, something that stuck with me. When heat is mastered, intelligence is unleashed. Just kind of mull that over.
Yeah, and maybe think about this too. Where else are fundamental physical limits like heat holding back progress? Not just in AI, but in other areas of high-performance computing. What kind of breakthroughs in cooling, maybe things we haven't even imagined yet, could unlock possibilities that seem